Hey everyone, I thought I'd go ahead and upload this video for chapter 11. This is planetary moons and rings. And like I normally do in lecture, I like to start off with the learning goals for the chapter. So the learning goal for chapter 11, learning goal 1 is compare the orbits and formation of regular and irregular moons. You'll see that's probably the simplest thing you'll consider in this whole chapter. Learning goal 2 is to describe the evidence for geological activity and liquid oceans on some of the moons. Learning goal 3 is to describe the composition, origin, and general structure of the rings of giant planets. And then finally, learning goal 4, explain the role gravity plays in the structure of rings and the behavior of ring particles. So let's get started on that. I'm going to start by sharing my screen. And I'm going to choose this one right here. So we should be able to see that. I want to shrink this so I don't take up so much of my screen space. And let's show the slideshow. Okay, so planetary moons and rings. So here's a wonderful picture of Saturn. Really nice picture. Not the most impressive in terms of showing the rings, but it is a really beautiful photograph. As you'll see, we have a photograph in your textbook where they show a backlighted Saturn picture. That's quite nice. And when you have it backlighted like that, you can see the dust and particles that are, on the order of comparable to, or maybe dozens of sizes of the wavelength of the light that you're looking with. So why do some planets have rings? That's a big question we're going to answer here. What is the difference between regular and irregular moons? Are all moons geologically dead? Where do rings come from, and how does gravity affect the structure and behavior of rings? So these are sort of parallels to the learning goals that we discussed. For starters, regular moons are basically ones that orbit in a plane that's very close to the equatorial plane of the planet and orbit in the same general direction, and they usually have fairly circular orbits, not elliptical. Irregular are the ones that more often than not actually rotate in a retrograde motion, in other words, the opposite direction that the moon actually orbits, or that the planet actually orbits, excuse me. And they are often very elliptical and inclined to the plane, the equatorial plane of the planet. So let's get started. So here's some moons. You have Io. You have this one that's so small. I think that's Iapetus. You have Io. Then you have this guy right here, Enceladus, excuse me. So there are dozens of worlds of rock and ice orbiting other worlds that exist in our solar system. Some are large, some are small. In fact, latest count in 2009 was over 200 moons. Just last year, 2019, excuse me, that was 2018, not 2009. In 2019, last year, I think the number of Saturn moons jumped, confirmed moon jumped to around 96, which put it higher than Jupiter, but then Jupiter came back and had like 124 or something. You can check that on the BBC's Sky and Night podcast is where I heard that reported. So some are large, some are small, some are rocky, some are icy, some are all sorts of stuff. You can see Io there in the middle. That actually looks sort of like a planet rendition of hell. It's actually quite sulfurous and stuff like that because it's actually superbly volcanically active. So the moons vary widely in their type of atmosphere and their volcanic activity. In fact, some moons have very, very little wispy moons, if any at all. I mean, atmospheres, if any at all. But then a couple have some really nice thick atmospheres. For instance, Titan has an atmosphere thicker than the Earth's. Some moons have icy surfaces, while others may have liquid water under the surface. There seems to be, by our models, a lot of those. So here's the moons, the major moons that we're looking at. You notice Mercury, and all these are on the same scale, by the way. So you can see Mercury is pretty good size. It's slightly bigger than Earth's moon, for instance. And even Earth's moon, of course, is bigger than Pluto. And Pluto has a moon that's Charon that's actually about half the size of it. So that's a pretty big moon compared to the mother planet's size, even though Pluto is not a planet. But you see, in fact, that Ganymede is bigger than Pluto, as is Titan. So Ganymede, these 4 moons that you see on the top left are actually the Galilean moons, which Galileo named the Medicean moons. They're Io, Europa, Ganymede, and Callisto. Io is the innermost one, Europa is the second, then Ganymede, and then Callisto is the farthest out. And in fact, they're in an orbital resonance of 1, 2, 4. So that's kind of interesting. We'll talk about that a little bit later. Saturn has its biggest moon, Titan. That's the one with the atmosphere. It's a pretty big deal. We also have smaller ones like Mimas and Enceladus. That was one we were just looking at, and Tethys and Dione and Rhea and Iapetus. That was not Iapetus that I saw earlier. It might have been Mimas. Can't remember actually. Your book will have a photo of it probably, and if they do, they'll tell you which moon it is. Let me see if I can look it up real quick, just because I hate making a boo-boo about the name of the moon, or even a rock like that was. Yeah, that Enceladus, I was right about that one. Of course, I was right about Io. Everybody knows that one. That was Phobos. I should have known better than that. So that's Phobos. That's one of the moons. This rock one over here, that's one of the moons of Mars. Mars actually has 2 moons. It has Phobos and Deimos, and Phobos is just obviously really small. So that's Phobos on the far left, Io, and then Enceladus on the far right. It's got the tiger stripe. That's why I remembered it. And then, of course, you look at Uranus. It has Miranda, Ariel, Umbriel, Tatiana, Oberon. Neptune has Triton. So there's a lot of moons. And like I said, a count is basically well over 200. Moons are made of rock, ice, or both. Some were formed by accretion and differentiation. Some were formed by collisions, just like our moon was is supposed to be created by some kind of collision. They have many diverse properties. The main thing is if they're formed by accretion, they can actually, if they get massive enough, they'll become molten, and then differentiation will occur, and their inner parts will be more dense. And as you get further and further closer to the farther and farther from the center and closer to the outer crust, the densities of the materials get smaller and smaller. That's if the differentiation process occurred, and that differentiation process results in actual energy that can be used to fuel things like tectonics and volcanism and so on and so forth. Most of the large moons in the solar system are regular moons, meaning that we don't think they were actually captured. We think they were probably part of a accretion disk, if you will, around the planetesimal when it first formed, and slowly they accreted into a bigger moon structure that stuck together. Whereas the irregular moons, as I told you, had the elliptical orbits. They're out of the plane. They were more than likely captured. Regular moons orbit near the planet's equatorial plane. They are close to the planet and travel in nearly circular orbits. They form from an accretion disk while the planet was forming. They revolve in the same direction the planet rotates, and most are tidally locked. Remember, that means like our moon, the same faces the planet. And examples of regular moons are Jupiter's Galilean moons and Saturn's Titan. Of course, there's several more. 2/3 of the moons in the solar system are irregular, whereas only 1/3 is regular. The properties of those have a more elliptical orbit. They're more inclined orbit. They're more distant orbits. They're usually retrograde orbits, captured bodies. There seem to be captured bodies that formed elsewhere in the solar system. Many are small, only a few kilometers across, and then the largest is Triton, which is a moon of Neptune, which you can see down here, and actually has a sort of a cantaloupe surface to it. So these are how the orbits look as well. You can see they're significantly different from the rather circular orbits that we get for regular moons. So the giant planets have several large moons, and many are larger than Earth's moon. Like I said, Mercury is now that we've excluded Pluto, is the smallest of the planets, and it's bigger than our moon. So I already told you Callisto and Titan are bigger than Mercury. Ganymede is just a bit smaller than Mercury. Some are geologically active where others used to be. They have surface markings, craters, and bright and dark areas, and those craters and surface markings can reveal geologic activity. For instance, if you see a crater, but then you see an area where it's not cratered, that non-cratered area suggests that that is a newer part of the surface. So something must have erased some of the craters that used to exist there. That something could have been cryovolcanism, which is a type of volcanism that takes place not with hot magma, but with warm ice that has become liquid. Bright and dark areas can show geologic activity, including where ice from below is crumpled up above when things sort of like plate tectonics going on, or just basically shifting of the ice patch on top. So moon categories are active now, possibly active, active in the past, and then never active. So we're going to see examples of those. Internal heat is necessary for a moon to be geologically active, and generally speaking, the amount of heat something loses is directly proportional to the surface area, and the time that the amount of heat it has available to it is basically directly proportional to the volume. So if you divide the surface area by the volume by the surface area, you'll get the radius, because the surface area is r squared and the volume is r cubed. So when you divide r cubed by r, you just get, or by r squared, you just get r. So what that means is the larger the radius, the more likely you are to have internal heat. So if you find something that, like our moon, are smaller, we know our moon's geologically essentially inactive. So if you find something smaller than that or comparable to that that's geologically active, there's something got to be going on other than just the internal heat. So, well, other than naturally occurring internal heat, let's put it that way. So in the case of Io is not that big of a moon, but it is pretty good size. It is the most volcanically active place we've ever seen. We've literally seen thousands of volcanoes going off on the surface. I think it's thousands. It's at least several hundreds from the various missions we've sent over. We've even flown over it and seen two major eruptions at the same time. So it's a pretty volcanically active area. When you actually look at it from a size standpoint, it shouldn't be geologically active, but when you realize that it's in a 1:4 ratio with Io, Europa, and Ganymede, what that means is every time Ganymede makes one orbit, Europa makes two, and Io makes four. So basically, every quarter orbit of Ganymede, Europa and Io are lining up. So that tends to stretch the planet. Remember, they're tidally locked too. So that tends to stretch the planet along the axis connecting the center of, stretch the moon along the axis connecting the center of the Earth and the center of the two moons. And then at other times it stretches it the other way. That tidal stretching back and forth is enough to generate the heat to account for basically the volcanism that we see. So basically, if you try to take a let's say a paper clip and you bend it back and forth, 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 you might even bend it enough times where it'll actually break. But if you notice before that, once you've done it several times, you touch the actual paper clip and the paper clip becomes quite hot. So that's sort of the same thing that's going on with Io as it's forced to compress and contract along different axes. So Io is the most volcanically active object in the solar system. It's slightly larger than our moon, so it's hot from tidal stretching. It has hundreds of vents and active volcanoes. Vast lava flows, volcanoes, and volcanic craters cover the surface. There's no impact craters. In fact, at one time I did a calculation that suggested the whole planet could be resurfaced in a matter of a few days or something. Silicate magma eruptions. So we basically can see the eruptions putting out some dark stuff, and we suspect they're probably silicate in nature. Bright carbon dioxide snow, and mountains twice as tall as Mount Everest. So even though that thing's slightly bigger than our moon, it has mountains that are twice as tall as Mount Everest. That's pretty impressive. Then we have Europa. Europa is a moon of Jupiter, and you can see on here this is a surface, and that looks very icy to me. In fact, what that is basically an icy surface, and that icy surface probably expands and contracts all the times and leaves cracks and stuff like that. So you get this cool look. It's geologically active. Its properties are slightly smaller than our moon. It's heated from tidal stretching again. Remember Io, Europa, and then Ganymede. So Europa is on that 1:4 resonance orbital as well. Only it happens, to be further away than Io, and only gets the bang, if you will, twice a cycle as opposed to 4 times a cycle like Io does. Again, it's not quite as hot as Io, but it's composed of ice and rock with an iron core. Its surface contains very few impact craters, so that suggests it's a very new surface. That's why we think it's active. The crust looks like broken slabs that have shifted into random positions. We believe it has a subsurface salty ocean. Model suggests that the icy surface may be tens of kilometers or even 100 kilometers thick, and then there'd be a salty ocean under it. It has a weak variable magnetic field and even has water geysers. So that's kind of some cool stuff to think about. Enceladus, which is a moon of Saturn, there's one with the tiger stripes. It's also active. Its properties are that it has a partially young surface. So what we mean by that is if you look over here, you see all these craters. But if you look over here, you see hardly no craters. So this part right here seems to be fairly young. This part seems to be fairly old. It experiences cryovolcanism. So we do have sort of volcanoes. You can see geysers shooting out every now and again. Radioactive decay in the core and tidal heating may provide energy. So radioactive decay is just like how the Earth gets a good fraction of its energy. Then tidal heating is not something Earth experiences, but sort of like Io and Europa do. Ridges, faults, and smooth plains on the surface, and it also probably likely has a liquid ocean under the icy crust. Titan is the moon of Saturn that has an atmosphere, and we've actually went there once. This is a cool photo from it. It actually looks like Mars. Some of the photos we've seen of Mars, and these are like ice rocks. These guys right here, but the atmosphere is so thick that it's a lot higher pressure than we experience at the surface of the Earth. It's the largest moon of Saturn, and like I said, it's geologically active. It's bigger than Mercury. It's got a thick nitrogen-rich atmosphere. We think the nitrogen richness came probably from ammonia being photodisassociated. So when the sunlight hits ammonia, which is NH3, it releases the ammonia, or excuse me, releases the nitrogen from the ammonia molecules. It also breaks up methane that way, and the methane can cause carbon and stuff of that sort. But it is, like I said, bigger than Mercury, has a thick, rich nitrogen atmosphere. It's probably orange because of hydrocarbon smog. It has methane lakes. So that's kind of neat. Lakes made out of liquid methane. You can imagine it has to be very cold for methane to be a liquid. Near absence of impact craters, which suggests it's a new surface. Again, that's more evidence that it's a active moon. Terrain similar to Earth. It has heat from radioactive decay. It has potential cryovolcanism, which is the source of fresh surface methane, because methane is one of those molecules you don't produce. You just sort of have it or you don't have it. And if you produce it, it's usually a result of life. That's one of our indicators of life. But the deal is with Titan, we think it has plenty of methane still below the surface, and cryovolcanism could release that methane. But if you let this go over long enough, the methane will eventually just disappear. Liquid ocean under the icy crust. Surface has icy rocks, and it has a methane water cycle, if you will. Triton, which is a moon of Neptune, that's the one with the cantaloupe surface. You can see the cantalouping type surface here. Looks fairly new, some cratering and stuff over here. Triton has a young surface, which shows that it is geologically active. It has terrain like a cantaloupe. Skin shows geologic activity. It's an irregular moon, so it's, even though it's quite big, it's probably a capture because of its irregular classification. It is in retrograde orbit. It has nitrogen geysers, methane and nitrogen ice surface, and it even has volcanic plains, which suggests it's got volcanism of some sort or had volcanism of some sort. Ganymede, which is another moon of Jupiter, Io, Europa, Ganymede, and then Callisto, of course, is the farthest one out, but Ganymede's the third farthest of the big Galilean moons. Ganymede is an example of a formerly active moon. So we don't think it's active now, but it was active in the past. The heat source powering geological activity was from differentiation, i.e. when it became molten, the more dense stuff sank to the center and the less dense stuff floated up. The properties are that it's larger than Mercury. It has a lot of impact craters, which suggests an ancient surface. It's fully differentiated, and the bright terrain is from some unknown past tectonic processes. So we don't know what happened, but something happened. But the fact that you still have quite a few craters suggests that, yeah, well, maybe this one is kind of old and geologically dead. This moon is Mimos. It's actually looks like the Death Star to me, but that one's kind of cool because the thing's not that big, and that crater is about a third of the diameter of it, so it's pretty impressive. Other formerly active moons. Other moons show signs of the surface of being formerly active, including bright and dark areas and tectonic fracturing. Examples are Dione and Mimas of Saturn and Miranda, Ariel of Uranus. So this is a pretty cool photograph. I always like that one. Like I said, it just looks like the Death Star. Callisto, which is that fourth outermost Galilean moon, shows no sign of early geologic activity, which is odd because it's really, really big. It's the third largest moon, yet we don't seem to think that it ever had enough energy to be geologically active. Its properties are its dark, heavily cratered surface. It has bright regions where subsurface ice has been exposed after impact. This one might also have a subsurface ocean, kind of weird. Other geologically dead moons include Umbriel of Uranus and Hyperion of Saturn. Look at that thing. That looks like coral or something. It's pretty nasty. Anyways, as you're going through your book, you can pick up all these different photos and look at them closely when you have more time. Ring systems. So the properties of ring systems, well, it turns out all four of the gas giants have ring systems, and we initially, of course, discovered Saturn's rings. Even Galileo noticed those. Later on, Herschel was able to envision them even better, and he thought it was actually a solid disk. Later, James Clerk Maxwell showed that it was basically impossible for them to be solid disk. He's the one that basically showed that they had to be individual particles. He's also the one that wrote the four equations that explain all we need to know about electricity and magnetism. The ring systems, like I said, are around all four of the giant planets. We slowly started discovering that through the 80s. In some cases, with stars being blocked or occulted, if you will, by Jupiter. And then we saw the light of the star flicker as it went behind the disk of Jupiter, and then as it appeared again from behind the disk of Jupiter. And then later it was confirmed, and we've done the same thing with Neptune and actually done flybys and seen. Sometimes we thought it was just arcs or parts of a ring, and then we actually did flybys and found they were complete rings. So that's kind of cool. They basically consist of small orbiting particles like the size of grains of sand all the way up to the size of large houses. But Saturn's rings are the largest and the brightest. They have all these different parts. They've got gaps and rings and shepherd moons and all sorts of cool stuff that you can learn about. And it turns out that they're basically temporary in nature. If we come back 4 billion years from now, we might not have the pretty rings that Saturn has right now, maybe even 1 billion years from now. But we also find out that there's sources that can feed the rings. For instance, moons that erupt like Io. We know that feeds some of the rings and some of the torus of Jupiter. We know there's some moons within the actual ring system that make the gaps and make little sub rings all by themselves. So it's kind of a neat, interesting area to study because you can study, orbital mechanics and see in real time how it's affected because you have all these millions and millions of particles, compared to moons. Here's the parts of the moons, or parts of the rings. So you can see the top one is Jupiter, then Saturn. I'll talk a little bit about Saturn just because it has some very specific parts. Cassini was an astronomer who used a better telescope and actually saw this gap right here, which we now call the Cassini gap. Later, we found the Encke gap and the Keeler gap, but basically A is the brightest of the rings, and it was out here. We thought A, B, basically all that was one big ring, but later we discovered no, the brightest one is actually A, and it's separated from B by the Cassini division, and then we later found C, which was much dimmer, and that's inside of B. And then we found D, and we've actually found no clear demarcation between D and C, or even between D and Saturn. It might even be that the particles in D are slowly burning up, causing really cool meteor showers on Saturn. Later on, we discovered E and G and F, all those rings, which are very, very wispy, and there's even ones that are further out than this. You can see the Jupiter rings are nowhere near as impressive, nor are any of the others, but they do have names and stuff of that sort for all those rings. The ring particles do follow Kepler's laws. That means that the ones in the smaller orbits are actually going faster and their period is smaller. I think with Saturn, I think the shortest periods were like 5 hours and 45 minutes, and the longest were like 20 hours, somewhere around there. So that gives you some idea. But that's the very point that Maxwell was making when he said if that disk were really a disk, then it would be torn all to pieces because the inner part has to go faster than the outer part, and that makes it not very uncomfortable for a rigid body. The vertical motions either cancel out, basically ramming into other things and the net momentum being zero, at least perpendicular to the plane, are leaving particles and leaving the particles moving in a plane. And the larger moons can affect the orbits. The moons can pull particles toward them, causing a low density gap. Shepherd moons can also herd particles into narrow rings. So if you have a particle, or excuse me, let's say you have a ring. Let's say there's a ring right here, and then there's a moon here and a moon here. This ring right here, remember, this is going faster than these. So this guy is tending to slow down this one. It's stealing energy from it. And since it's stealing energy from it, it's going to make it want to drift out here, whereas this one's actually going faster, so it's actually applying energy to it, which makes it want to go further out. So you can actually get two moons doing that, and that's how they shepherd it. You either steal energy. The outer moon will steal energy from the ring, or the inner moon will add energy to the ring. Adding energy is basically equivalent to speeding up. If you speed up, that means you're going to drift out. If you slow down, or if you lose energy, that means you're going to lose speed, and that means you're going to fall in. So this guy tends to force them in, this guy tends to force them out. So you end up getting a nice little ring in between them. This is not the perfect case. This is actually a totally different example that they're using, but you'll see one later. Material found in planetary rings is probably the result of tidal stresses. Basically, we think they occur within what I told you guys about before, called the Roche limit. So there's an area within a certain number of radii from the planet where the gravitational attraction between the north pole of the planet and the south pole of the planet, pulling two different directions on something on an object outside of the planet, that is actually stronger than the self-gravity of two particles trying to stick together to make a moon. Wherever that happens to be the case, and where it stops being the case, is what we call the Roche limit. So anything that tries to form within, i.e. at a closer distance than the Roche limit, tends to be torn apart. So you can sort of think of the ring particles as particles that would be maybe a moon, but the Roche limit dictated that they couldn't stick together. So the gravitational force is stronger on the side of an object closest to a planet than on the more distant side. The Roche limit is the point at which the tidal stresses are greater than the self-gravity of a body. Now that doesn't mean like, Elon Musk couldn't park a Tesla in the rings of Jupiter. He certainly could, because the forces that hold the atoms and molecules together of Tesla are stronger than self-gravity. So it's just specifically about things that are stuck together because of their self-gravity. A moon or planetesimal that comes within the Roche's limit is pulled apart into little pieces. The pieces spread out, the orbits circularize and flatten, and the pieces are distributed around the planet in the form of a ring. Ring composition is the same as the composition of the moons they come from. So basically, if it's an accretion disk, it's an accretion disk made of the stuff that would have otherwise made a moon. So yeah, that's what the rings are left over, unless they get an extra perk from a more distant moon, say, and that occasionally occurs. Saturn's rings are bright and are mostly water ice, whereas Uranus and Neptune rings are dark and mostly radiation darkened organic compounds or materials. So basically the dark ones means they're organic, and the sun photodissociates the organic compounds, which releases the carbon, and the carbon is just like graphite from a pencil, or the black stuff that you get on the snow when you drive your car in the city after a snowstorm. So over time they become black and sooty. So Uranus and Neptune's rings are like that. They're sort of black and sooty, whereas Saturn's has these wonderful bright rings that are made basically of water ice. Jupiter's rings are intermediate because they're rich in silicates, like the inner moons. And moons can contribute material through volcanism, as I talked about with Io, and Enceladus it happens as well. Saturn's rings were first seen by Galileo in 1610, but not recognized as rings. Huygens in 1655 used I think I said Herschel earlier. I apologize for that. I shouldn't have said Herschel. It was Huygens. Huygens in 1655 used a better telescope and recognized them as rings. Remember, Galileo said they look like ears. But Saturn's rings are a very complicated system composed of thousands of ringlets, each made of tiny orbiting particles, and they all obey Kepler's laws, of course. There are bright and dark rings and gaps and divisions. So you can see the inky gap and the Cassini division and the A ring and the B ring. Remember, the A ring and B ring are separated by the Cassini division. That's about the only trivia type question I'd ever think about asking you about the parts of the ring. I might ask you actual sciencey questions about, what do shepherd moons do or something like that, but I wouldn't never ask you about, what caused the inky gap? So gaps are not empty. They just appear that way because they're less densely packed. You can sort of think of movies when you see people going through asteroid belts. Those are not accurate. As I told you before, asteroid belts are surprisingly low density areas. Maybe flying through a ring of Saturn would be closer to what movies represent as flying through an asteroid belt. Flying through the dark gaps would be more like flying through an asteroid belt. So the brightness or darkness reflect the amount of material in each ring. Though wide, the ring system is extremely thin. If Saturn's rings were as thick as a piece of paper, the rings would be 6 football fields wide. So that gives you an idea of what the ratio is. It's like a really, 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 really thin pancake. So the diffuse rings are fainter and have no defined boundaries. Saturn's largest ring is a diffuse dust ring discovered in 2009. Notice there's the orbit of Phoebe right in the middle and Iapetus inside of that. And then there's this huge ring way out here. This is that backlighted photo I talked about earlier. When you have Saturn backlit, you can see a lot more texture to the rings because, again, these particles making up the rings are basically on the order of a few wavelengths to a few dozen wavelengths, so that the light's not actually messed up by it's not reflected back. It just comes right through it. It's sort of like backlighting when you see that picture of a cat in your textbook. The E ring and G ring are also quite diffuse. Here's two shepherd moons, Pandora and Prometheus. And you can see, Prometheus is on the inner track, Pandora is on the outer track. And you can see these little waves coming up behind them. There's other areas where the rings will actually have a scalloped pattern. So the shepherd moons can distort the rings. They can also, maintain them a little bit by forcing the rings to be well organized in between the two moons. Gravity can cause distortions, including what look like twists and waves. That's what's going on there. There's the scalloped area I was talking about. Let's see how it's Other distortions include scallop shapes and appearance of transient spokes in Saturn's rings. Spokes grow in a radial direction, so spokes would be coming out from the center of the planet out towards the edge, perpendicular to the surface of the planet, if you will. So they last for less than half an hour orbit around Saturn, indicating that the particles in the spokes must be suspended above the ring plane, probably by electrostatic forces. So that what they're thinking there is it might be related to the gravitational fields, because lasting a half an orbit means that it really depends on its position relative to the planet. So that's kind of important, but we really just don't know yet. So there's the backlit cat I was talking about earlier, because these the hairs are on the order of a couple to a few dozen wavelengths in thickness, so it's backlit just like Saturn is. The rings of the outer giants are mostly narrow and diffuse. Backlighting brings them into view. Neptune has denser sections known as ring arcs. In fact, when we first saw them, we just thought they might just be ring arcs, but later when we flew a mission, I think it was Voyager 2, but your book will tell you exactly which one that was. Voyager 2, when it went by, confirmed that they were in fact complete rings, not just ring arcs. Rings do not last forever. Collisions and sunlight destroy the rings, so collisions with other particles makes them smaller and smaller, makes them lose energy or even gain energy. Both of them cases, losing energy means they're going to get closer and closer to the planet. Gaining energy means they're going to move farther and farther away, and then the sunlight can actually destroy them by breaking up the molecules. Shepherd moons can help stabilize the rings, and then orbital resonances can actually create the gaps. For instance, I think the inky gap is a result of Enceladus, I want to say. Your book will mention that. I wouldn't ask you that type of question because I don't remember those things always off the top of my head. But just, keep in mind when you see that stuff, a lot of times orbital resonance is where basically once every one orbit or once every two orbits, something in that gap would be lined up with the centers of Saturn, thing in the gap in the center of the moon. And that slowly would tug that thing farther and farther outward till that that gap became empty. So that's sort of how the orbital resonances work. Well, that's about it. I hope that was somewhat helpful for you guys. As always, read The Process of Science. Feel free to do any of the things at the end of the chapters. And that's about it. I'll be posting this in a few, and I will talk to you guys tomorrow.